Hi, welcome to Crossroads. Thank you for joining us once again, just like every month, to think about what intelligence is and what parts of science can help us answer our questions about its mechanisms in mathematics. CrossLabs is a research institute in Kyoto and Tokyo that's aimed at understanding the mind through computational research. We explore ideas about brain science, information sciences, artificial intelligence, and artificial life, and how they can enable new technology and changes in society. The Cross and Crossroads means we go interdisciplinary with this monthly fun public forum on the sciences of the mind and intelligence. Crossroads and Cross Labs are supported by Cross Compass, which is a leading AI company in Japan working in technologies such as manufacturing. Before we start, I want to give a special thanks to Olaf, Antoine, Stephen, Oneris, Katsu-san for helping out with all of this. Um, and as usual, our format is going to be, we're going to have three parts of our talk. First, we're going to have our talk by our special guest today, Dr. Alyssa Adams, followed by a question and answer session held here on YouTube Live, and then an off-stream discussion. So today it is my pleasure to introduce Alyssa Adams, who is a postdoctoral fellow at the Morgridge Institute for Research at the University of Wisconsin-Madison. And the topic today will be Emergence, the force behind open-endedness. Alyssa?
Great. Yeah, thank you so much. I appreciate the lovely introduction. So, yeah, with that, I guess we'll just dive right in. So, let me make sure I have. All right, we're good to go. Yeah, so I have got a lot of background in physics. I got my PhD in physics, but I actually just really fell in love with biology. So, particular, I really fell in love with this idea of open-endedness and emergence in biological systems. So, I also noticed that as a physicist, I'm really used to having a lot of mathematical models to explain how things change and evolve over time, particularly things that are moving around in space, like the stars and the planets. You know, we have Newton's laws of physics. We also have Einstein's equations and things like that. But we don't have anything like that for biology, and that's where I'm really excited because I think we can do a lot of really cool work to come up with some sort of mathematics that can describe what biology is doing and what makes living systems different than non-living systems. So, a little bit more specific, I study this intersection between the theory of computation, physics, information theory, and biological evolution. So, things like machine learning. I'm also looking at the interactions between viruses and their hosts in bioinformatics and different other biological interactions. But really, at the heart of it, I'm thinking a lot about philosophy. So, if I'm thinking about a new mathematical framework for living systems, it's not just something that would be like a Voltaire equation, right? It would have to be something that can accommodate and explain mechanistically and very precisely things like open endedness, emergence, complexity, and evolution. So, something that's a lot like a calculus, but can explain these kinds of things that make living systems very unique from non living systems. So I also have a picture here of Times Square, New York City, from an airplane. And every time I get on an airplane and I look out the window, I'm always just struck by how different like human areas look than the rest of the world. I mean, it's very obvious where humans live because we transform our environment and we transform the world. And we also like work in like grids and geometric shapes and lights and all kinds of different things. But I'm always fascinated to know like why does it look the way that it does? Because if we looked over the Appalachian Mountains, for example, or some places that don't have a lot of buildings that look like New York City, both are teeming with life. However, the two systems look completely different than each other. And I find that really interesting. Okay. So, for the first part of my talk, what I want to talk about is tools and gadgets and gizmos because I think they're really fascinating. And I actually think they have a lot to say about biology and how living systems operate. So, I have a picture of these fun prism glasses, and I don't know if you've ever had a chance to look through them before. So the way that they work is that they're paper glasses with some sort of like plastic film for lenses, and you put them on, and everything that emits light will also emit these rainbows that are coming out of it. And in high school chemistry class, I remember our teacher passed these out. I put them on, and then she asked us to look at these. I think they were in like glowing tubes or like tubes with different I don't know, chemicals in them and or looking at flames of things burning. And she wanted us to see how those rainbows are changing in appearance by looking at different elements. And I always thought that was really, really cool because as I put these glasses on, not only am I looking at the world differently, but I'm changing my visual state space in which I'm operating. So before, when I don't have my glasses, I see things in the way that, I'm used to seeing them. But all of a sudden, when I put these glasses on, I am operating in a state space with additional variables. So not only can I see everything that I was seeing before, but I can see these new rainbows. And depending on what kind of element I was looking at in chemistry class, it would tell me what particular element it was, depending on the what the rainbows look like and how those colors changed. So I thought this was really cool because, hey, what if we could just do this innately? And if we could do this innately, then how would that change our world? So, so say we could do this innately, right? And we could see everything in rainbows. And what would our TVs look like if we could see this way? How would it change what billboards and advertisements look? And what about clothing? You can imagine like we could design something really cool on a T-shirt where it plays to this element of this state space that we can access, right? But going backwards, like say we were able to change our visual state space in a different way. So maybe we can't see through air, right? What would our world look like then? Um, there's no reason why we wouldn't be able to see through air, but just pretend. Well, screens wouldn't be useful or effective or anything like that, and things like billboards probably wouldn't be very useful at all. So our world would probably look really different. So it really got me thinking that tools and gadgets and things that we can invent, and also organs and sensory organs and things like that, are really determining how we're interacting with our world and how we are able to change features about our world that we interact in. But it's not just about things that you can hold in your hand, like an eyeball or some glasses or things like that. It's also about mental models as well. So you can think about things like language is a mental model, and things like culture and ideas and all like stories and other ways that we're able to describe our world. So we spend a lot of energy and effort in education and educating, especially young people, to be able to operate in the world that we've created because we have all these social rules and social constructs, and we want to be able to make sure that new people who come into the world, or most new people who come into the world, can navigate this system as well. So it's not just an external tool. There's also internal tools as well. But regardless if they're external or internal, they're both physical states of an agent, or they're physical extensions of an agent. So in the case of a mental model, I've been told by a lot of people who study the brain that it's a that repetition for learning is really important because it creates these neural grooves or neural pathways and things of that nature, and that's a physical state of the brain. And I also had a neurologist tell me that the weights between neurons definitely matter, especially when it comes to learning and tasks. So tools are like physical things that we can look at. So here's a really explicit example for a mental model that has real physical implications in the world. So the ancient Greeks, never described blue at all in any of their art or in their literature. And in fact, Homer, when he was writing, like in the text of the Iliad, actually described the ocean as being a dark wine color. And at first, researchers were thinking, well, maybe the optic nerve didn't evolve to the point where they could see blue yet. But that theory kind of got tossed out the window because what it seems to be more accurate is that they just didn't describe they just didn't describe color in that sense. Like they described color experiences made out of movement and shimmering. So they didn't necessarily really care about blue. Like we care about things like hue, saturation, brightness, but the ancient Greeks, they didn't use that mental model to describe the world. And as a result, you can see how the art and the literature changes to reflect that. And I like to wonder, what would the ancient Greeks look like if they had our mental models of color, but also how would our world change if we had the ancient Greeks' mental models of color? Our world might be quite different than it is today. And if you want to learn more about this, you can check out this really cool essay on Aeon from 2017. So, tools. There's also this really cool essay about screwdrivers by Stu Kaufman that I really, really like. So, what he's trying to argue is that there are way more uses for a screwdriver than you can ever calculate. In fact, he says, if you ask me, a screwdriver is actually just a can opener. Usefulness is in the eye of the beholder, and it's not a math formula. And I think this is really cool because not only does the use of a tool depend on the state of a tool, right? Like, it's a screwdriver, it's the shape determines like the function, but it also depends on the environment that I'm in as well. So like if I were to go through IKEA and it's a post-apocalyptic world and I had a big screwdriver, I might be tempted to use it to smash all the glass cups, right? Or if I'm on the surface of Mars, the number of uses that I have for that screwdriver are completely different. But it also depends on the state of the user as well. So if I'm like a trained mechanic, I might come up with different uses for the screwdriver than somebody who was raised by wolves, for example. So tools can either be created or evolved. So humans are really, really good at creating new tools. I think that's what makes us so interesting because we're able to see a problem, create a tool in order to address that. But a lot of what happens in the rest of biology is that tools are evolved. And what a tool is doing, just like those glasses that you might have used in high school chemistry class, is that it allows you to access a new state space. But more specifically, it allows you to translate one state space into another state space. So, for the example of a screwdriver, if I'm using it in the way that it's intended to be designed, it allows me to access the state of a tight screw, which I can't access without the screwdriver. I mean, I could try to pinch it with my fingers, but I'm not going to get it very tight or as tight as I want it to. Temperature is like the idea of temperature, as like a Fahrenheit or Celsius, is also a tool that we use. So, the concept of temperature in thermodynamics is really talking about like the average movements of particles of like atoms or an ideal gas, right? That's moving around in a room. But the thing is, we don't have anything to measure that directly, right? I mean, I cannot, with just the tools that make up me, go around and measure the position and velocity of every molecule of gas that's going around in my room. It's just not possible. So it takes something that would be not accessible and it makes it something accessible. So if you have two people in a room and one says that, oh, it's so hot in here, and another one says, oh, it's cold in here, how are you going to be able to compare those two temperatures together? But what temperature does with thermometers is that it provides a way to normalize and compare subjective experiences with each other. So, okay, the whole reason that I wanted to talk about tools and gadgets and gizmos in the first place is because I wanted to convey this point that tools can either be internal or external physical states with respect to some sort of agent that might be using a tool. And an agent is using these tools to access new state spaces, right? Okay, so let's put tools on pause for a second. And the reason why I wanted to talk about this is because in 2015, I went to this workshop on reconceptualizing the origin of life. And during that workshop, there was this discussion about are biological states being discovered or are they being created? And I thought this is a really cool question that I still think about today. Because on one hand, biological evolution is creating new tools for new state spaces to be accessed. So on one hand, it's these states are and these state spaces are being created, but on the other hand, we also know that biological evolution is very closely intertwined with the environment. And a lot of people will say that evolution is about minimizing some sort of like energy or information or something like that between agents and the environment, and you want to minimize that so that agents are able to navigate their environment in the easiest way possible. So, in that sense, biological these entities are evolving according to the parameters that the environment is selecting upon. So, in order to answer this question, I would say that it's kind of both. Biology co evolves with an environment to create new tools to discover state spaces offered by the environment, right? But you might be wondering, okay, well, this is interesting, but what do tools, state spaces, and states and evolution have to do with emergence and open-endedness, right? So this is where I think it gets really exciting. Let me first talk about open-endedness, and then I'll tell you why I think emergence is so important to understand open-endedness, and why I think that emergence is the driver for open-endedness, right? There's this great essay in from 2017 about open-endedness being the last grand challenge you've never heard of, particularly with context to AI. So, currently, a lot of machine learning algorithms use novelty search. So, what they're doing is they're addressing finding new solutions to existing challenges open endedly, but they're not inherently generating new challenges, new kinds of challenges to be solved. And the most powerful open ended system would generate both. So, not only would it solve problems, but it would also create new problems for it to solve, right? And it turns out that there's all kinds of different categories of open-endedness. So it's not just like biological evolution is like the one and only kind of open-endedness. I mean, a lot of things that that biology does has different categories of open-endedness. Now, what I'm not going to do is I'm not going to really talk about them. But what I wanted to do is I wanted to highlight a lot of a theme that I see that is consistent throughout both ways of categorizing this. And what that theme is that I've noticed is this idea of innovation and creating something new, major transitions, new kinds of things, right? Um, Emergence, new kinds of entities, new adaptations, adaptive novelty, and things like that. And also, Emily Dolson has some really great stuff on how to measure these changes and how to measure open-endedness in systems. And a lot of those measurements have to do with finding innovation and new things in different state spaces to describe your system. And while I was studying open-endedness as a grad student, I was also studying this idea of emergence. And then I thought, gee, emergence sounds a lot like innovation. And so my hypothesis and the reason why I'm giving this talk is to argue that I think that emergence is necessary for open-ended evolution to happen. And in order to, I guess, like in order to explain myself a little bit, I'm going to talk a little bit about what precisely I mean by emergence, because emergence is a word that gets thrown around a lot and used in a lot of different contexts. Colloquially, emergence is usually quoted as this Aristotle quote, as the whole is different than the sum of the parts. I have to drink tea because sometimes I talk a lot. And after the pandemic of not talking that much, I'm not totally used to it. But usually this quote gets misquoted as the whole is more than the sum of its parts, but it's the whole is different than the sum of its parts. Okay. And the reason why that's different, sorry, why that distinction is important is because it talks. So sorry. I warned about this before this talk. I was like, oh my gosh, I hope I don't choke. Totally choking. So sorry. Okay. Anyways, so this is like the gestaltist idea, right, from psychology, where if you put pieces of things together, like those pieces individually don't necessarily mean that they're going to necessarily reflect what an observer is going to see as a whole. So, like, an example is like seeing, so sorry, one second. Maybe I'll try speaking slower. Okay, so to illustrate, imagine you see a plug in the wall. So each of the plugs, each of the holes in the plug, if you saw them individually, you wouldn't necessarily think that that plug would make a little face, right? But until you see that whole thing, all those parts together, then you might think that, that plug is kind of looking like a little smiley face. And so that's the idea of emergence, right? So, like, the individual holes in the plug don't necessarily mean that it's going to be a face, but if you put it together, somebody who's observing it might think that it looks like a face. Okay, in 1997, there was this really, really great paper about emergence, right? And there's two types of emergence that Mark Badeau wants to talk about. There's weak emergence, and then there's also strong emergence. I think it's really good to delineate the two because I think by doing so, you get this really, really interesting concept that relates directly to states and state spaces. With weak emergence, it's more like the cat emerged from under the bed or Ebola emerged once again. But what you're doing is you're taking a known state space and you're expanding it, right? So you're taking a set of possible states and you're adding to it. So, as an example, you can think of like the word state space, and you're expanding it by adding a new word. So, recently, there's been a new word coming out. It's called chuggy. This is a Gen Z word, and it refers to lame things that millennials do, such as being obsessed with Harry Potter or something, right? So you can imagine the word state space as the gray circle as being all the possible words that you could come up with, right? And then your blue circles are the actual instantiated words, the words that are being used. So like the gray circle is like, all the words that you could possibly think of that could exist. And then the blue circles are the words that actually do exist and are being used. And depending on like the different kind of language, you might get a different coverage of which sounds and possible words are actually being instantiated. So chuggy is adding a brand new word to it. So you have something. So you have like this new red dot. But with strong emergence, you take this idea even further. So you talk about the emergence of multicellularity, the emergence of language, or the appearance of something entirely new. So going back to the word state space example, so rather than thinking of spoken words, you can think of written words instead. So with hashtags, I guess like 30 years ago, if you had like a pound sign followed by a bunch of characters, you might think, well, that was probably a typo or maybe something that's like, I don't know, specific to a particular document or whatever, right? But what Twitter wanted to do is they wanted to expand that state space. So they latched onto that one particular word state, which is like the pound sign followed by some characters. And they were like, you know what? We're going to create an entirely new state space out of that motif. And so that's what they did by introducing all this new code and all this new stuff on their platform. So that rather than just thinking of words, now you're thinking of hashtags. So, if you want to learn more about emergence and a lot of philosophical implications, I highly recommend this book. It's super good and it's got a lot of really great essays. Okay, so going back to this idea of innovation, like, I'm making this claim that emergence is very related to this idea of innovation, which is very related to this idea of open ended evolution. More tea. Okay, so so in a system, we can ask two questions. How is the system discovering new states by using current tools that are available? And also, how does the system discover new state spaces, such as creating new tools, right? So, just as a reminder, a state is a possible configuration of a system given some sets of variables. So, example, red is a state, and a state space is the set of all possible states, like colors. In physics, we would also call this the phase space as well. So you also might be thinking to yourself, wait a minute. I thought if you're bringing tools into this whole thing, I thought tools are really hard because you can have an undefined number of uses for your tools. And I totally agree. It's a really, really hard problem to think about, but I do have a solution for that. And that solution is all about context. Normally, we don't usually think about the observer being directly in our models. I mean, we think about it with like agent based models and things like that. But I wanted to think about this idea very explicitly because also there was this idea before quantum mechanics called supervenience. And this idea of supervenience was basically saying, like, well, we want to understand how charges come together to create new things. So, like, the idea of supervenience was you take some sort of charged particle that has some sort of like, I don't know, field around it. You take another charged particle that has another field around it, and then you string them together. And then what you get is like you might get something magically new that's different than just the sum of the charges. Well, with the advent of quantum mechanics, that the whole theory was just tossed out the window because it's ridiculous, right? And doesn't make any sense for charged particles and for physics or anything like that. But actually, for biology, I think it's worth revisiting because if we think about something like a protein, right? You can string a bunch of amino acids together, and when you put that string of amino acids, it actually does become something that's different in context with its environment. So, like if you had a protein like Rubisco, for example, and it's just floating in space, like literally just in a vacuum, it doesn't mean anything. But if you take Robisco and you put it in a plant or something, suddenly it has a use, and its function is the function is different than the sum of the parts. So to expand on this idea a little bit, imagine you're an observer and you're looking at an object or a system or something like that, and you can describe that object in tons of different ways. In other words, you can access many different state spaces that describe the object. And the number of state spaces is huge, right? You could think of things in terms of color, in terms of weight, in terms of shininess. It's really totally context dependent and depends a lot on, it depends on the state of view, depends on the state of the object, and it depends on the state of the environment that you're in. But what you can do is you can actually access even more state spaces with additional modifications, like with tools like telescopes and things like that. Before telescopes, we weren't able to see stars very well, but with the addition of telescopes, we could see not only stars, but we could see planets, galaxies, and all kinds of other cool stuff. So we could access new state spaces with new tools. Okay, so pretend you're like, okay, I have my tool set, right? So you have a tool set, you're an observer plus your tools plus your environment. And what you can do is you can take all of the different possible state spaces and you can order them according to coarse grainedness, if you will. So like at the top, you can have your most coarse grained state spaces, and at the bottom, your least coarse grained state spaces. Now, the most coarse grained state space that I could possibly think of is the universe. Does the universe exist? Yes or no? As far as I know, it's a yes. So, that's as most coarse grained as I can think of, but maybe you're way more creative than I am and you can come up with something even more coarse grained, right? So, now what gets really interesting, I think, is understanding what state spaces are important, right? So, not all the state spaces that I can describe everything in are important or even useful. So, that means I can throw some state spaces away. And which ones can I throw away? Well, for example, I really don't care about how my mug looks next to Kim Kardashian. I can throw that state space away. I also don't care about the state space of, I don't know, like the corner, like the electrical charge on the corner of my lamp plus the electrical charge on the back of that paper airplane over there. I don't care. I can throw those away. But when I'm doing that, what I have to ask myself, why am I throwing it away? Because it's not useful, right? But but why? And the answer is because of computation. I can't compute anything with those states, any states that I want. So with computation, this is how I think about computation. You have a set of input states, and you go through some sort of processes to achieve some sort of desired output state. So going to back to the example of Twitter with hashtags, um, I'm a user, and my problem is I really want to see all the cat pictures in one spot. I just want to be able to scroll and see tons of cat pictures, right? But Twitter is like, oh, I see that. I see that users want to perform a particular computation. And the way that Twitter was set up before hashtags, you cannot compute that. Well, you might be able to, but it might be really, really hard in order to do that, to curate a feed that is just only cat pictures. So what Twitter said was, how can we design a new tool to let users organize tweets in order to see just cat pictures or something? But when I'm thinking about state spaces, computations, and things like that, I would reframe the question as how can we design a tool, right, to create a state space to allow users to perform computations to reach some desired state? And so when they created this hashtag state space, they also created all of the code and all of the features that you see in your apps in order to allow those computations to happen. So going back to this, if you think about it in terms of like a graph or something, where you have your blue circles as your states, you could think of computation as walking along your state space. And what you want to do is you want to be able to structure your system such that you're able to take a walk from your desired starting state to your desired final state. And that will allow you to do computation. So, wait a minute. How do biological systems do this anyways? Like, what does this topology look like? How do we even know like how many state spaces a biological object is interacting with? How many state spaces do I interact with? Like, what are the active state spaces that I'm using every day to perform computations? How many of them? Can I focus on many at one time? So, in order to ask these questions, we're going to need a telescope, right? We're going to need a new tool in order to be able to answer these kinds of questions. And the way that I see it, from my perspective, is that there's a lot of data out there, like with the internet. The internet is our telescope. There's social media, there's memes, there's technology patents, there's language, there's laws, financial systems, government, organizational structures. All of this we have data on of how these things are evolving and changing over time. So, what I would want to ask is, how do humans and other biological systems create and evolve new tools to operate in the world? So, in the future and my current work, that's what I'm hoping to do. Is I'm hoping to take real insights from real data in order to understand what these relationships look like. So, these relationships, once again, that I'm thinking of, is not just the state of the observers and not just the state of the environment, but what tools are they all creating? What state spaces are they allowing, or are they opening up and also closing at the same time? And what states are we operating in? And how are these relationships changing over time in order to get open-endedness? Okay, but so what, right? Like, let's be a little bit more concrete. Like, why would anybody want to do this? Like, so it all sounds like fun and everything, but what are the technological implications of doing these kinds of things? Well, going back to that article from 2017 about the last grand challenge you've never heard of course, one of the first things that comes to mind is machine intelligence. So, currently, machine learning models assume a fixed function between inputs and outputs. So, say you have a data set of your inputs, and and you also have a bunch of outputs. What you can do is you can come up with this machine learning architecture, in order to fit whatever that function is that's desired in order to solve whatever problem that you're trying to solve. So, and when you train and optimize your model, you're literally like shrink wrap fitting like plastic over your data in order to approximate whatever desired function that is. But the issue is that that function might be changing over time in reality. Because I know that a lot of different states, like if you have tools that are changing over time, then your functions that you're able to access and your dynamics of these systems are also going to be changing over time as well. So I think that understanding these different relationships would really help understand how machine intelligence can go from fitting fixed functions to looking like something where humans are creating new solutions to existing problems. So, in other words, having creative machines, machines that can actually innovate, just like the rest of biology does. So, what I would want to know is, can machines create new tools for us to use? Right? We're always coming up. We're always like creating these new tools for us to use. But it would be really cool in order to have or it would just be really cool to have a machine intelligence that would look at all of our technology patents and say, these ones are going to be the most innovative, and or maybe it even comes up with something all by itself. So, obviously there's like so much more. I mean, gosh, like almost every aspect of our human lives is touched by this idea of open-endedness. So, we could better understand and predict ourselves, like our own evolution, and how we structure the world, and how we evolve, change, and grow over time. I think these ideas touch a lot on economy, technology, evolution, communication, problem solving, and creativity. Like, if we understood open-endedness in terms of viruses, can we create vaccines before a pandemic happens? Like, can we just have vaccines ready to go because we're like, oh, we looked at all these viruses, we understand open-ended evolution, and we know that these viruses have a really high chance of looking like X, Y, and Z. Therefore, we're ready with vaccines. I don't know. I would be really interested in if to see if that's possible. And then, of course, we talked a lot about the environment and how systems interact with the environment, but I'm also thinking a lot about how we humans are interacting with our environment. Obviously, it's going terribly for us. So I would want to understand, like, how can we better understand our relationship with the environment, especially when it comes to computation, because computation takes a lot of energy. We're computing more and more and more all the time. Is there a way to optimize this energy use? And also, can we be able to can we accurately predict what sort of needs that we will have in the future, and to be able to anticipate big changes before they happen? And then, of course, absolutely, no shadow of a doubt, we could use this sort of mathematics and understandings to look for new life outside of our own solar system, or within our solar system, of course, and understand our own origin of life here on Earth. So with that, I'm going to pause and open it up for discussion. And thank you so much to everybody at Cross Labs, UW, ASU, and of course everybody here in the audience. Thank you so much. This has been so much fun. So I'm so excited to hear your questions, and I can't wait.
Thank you so much, Alyssa. And for those of you in the audience, if you have any questions, you can go ahead and ask them on Slido. We have the link posted over in the chat, so go take a look at that. But before we get to the audience questions, I'll start with one of my own. So early on in the talk, you talked a lot about tools and how things like sensors, for instance, can be kind of like tools. So how do you draw, I guess, a distinction or a delineation between like what's the tool and what's the agent? And where does it something stop being the agent and start being a tool?
That's a good question, and I actually think that agents are bags of tools. So, like, I would you kn I don't think there is, like, a really clear delineation there, and I know that there's a lot of really cool research, from the C4 group at Santa Fe, where I think they had just put out a paper about individuality and the thermodynamics of individuality, which seems really cool. But I don't really have, like, a clear distinction between an agent and, just a set of tools. And I have more to think about that, but I think there's a lot of interesting stuff that can come from exploring that, I guess. And it's interesting about, like, understanding, like, what constitutes an individual, because we understand individuality from our perspective, but I don't know, like, is it useful? Like, I mean, are there these pseudo agents that happen in biology, such as like viruses, for example, that aren't necessarily like a full agent themselves, but could act as an agent in some contexts? So yeah, it's interesting.
Okay, cool. Thank you. So we have our first question. So from an anonymous viewer who is asking if you could give some more examples of emergence. Like, I don't know if you have a favorite one or something like that.
Sure. My favorite example is actually a rainbow. I think a rainbow is a really cool example because it's just a cloud vapor, or a vapor of water droplets, and you have light passing through them, and as the light's passing through them, it's refracting through these water droplets and creating a rainbow. But it also depends, like, not only on, like, the angle of how the light is hitting the vapor, but it also depends on how the observer is standing with respect to that cloud. But also, it also depends on an observer's ability to see the colors that we know as being the visible spectrum. I mean,
Mhm.
there's absolutely no reason that well, I mean, there might be a reason, but, like, there doesn't seem like it had to be those particular colors that we saw. Like, what if we shifted our entire visual spectrum somewhere else? Would that change our concept of a rainbow? I'm not sure. But so that's my favorite example. But another example of emergence is collective ant behavior as well, and collective bee behavior. Those are always really cool. Ants, they will come together, and fire ants will create a raft to prevent themselves from drowning. And that's an example of emergent behavior from interactions between smaller agents.
Cool. Thanks. I think those are really helpful. So our next question is from Olaf. So computationally, if code A is output by code B and is made accessible to code B again, we seemingly close the loop. Where do we draw the emergence line?
Hmm. Let's see. I'm not really sure where emergence. Where Olaf? Do you know where emergence would happen in this context?
Yeah,
I don't
maybe
know.
that's part of the maybe that's part of the question. I don't know.
Oh, I
Um,
see. Yeah, good question. Let's see. Okay, so if code, could you read the question again? What
sure,
was
sure.
that?
So if code A is outputted by code B and is made accessible to code B again, we seemingly close the loop. Where do we draw the emergence line?
Oh, I see. Right, right, right. Yeah, that's. I think that's really interesting. Like the way that I define, or I define, like the way that I think of emergence is being something that is seen through, I guess, like through some sort of like a third party observer. But I'm not actually completely sure if that's totally right, because I think in this example, if you have code that's outputting more code, right? I think that's a really, yeah, I think that's a really good, oh, wait, no, because if it can be fed back into code B, then code B is its own, it's almost like it's being its own, observer in that point. So yeah, in that sense, I'm not really sure where it would draw the line for emergence. I guess it depends on what constitutes an individual in this case, and what each individual agent is like what state spaces are they being are being accessed, and can they change their state spaces. That's a fun question, though.
Yeah, I think a lot of this stuff's really, really nuanced, is what we're kind of
Yeah,
figuring out here. But that's what
totally.
makes it really interesting. Okay, so next question. Do you see any limitations to the state space model of computational discovery?
Yeah, I think one of the biggest limitations is that when I'm thinking about, well, at least when I'm thinking about state spaces, it's in a it's a discrete model, and it's not necessarily accounting for all of the smoothness between things, right? So, like differential equations is really nice because you talk about rates of flow, and you don't have to worry about like the discreteness of things. But where we have this idea of state spaces, I think counting can be a really big problem. How are you going to handle all of the different specific instances of in between state spaces that aren't necessarily being used? And I think one of the biggest limitations is it's really, really hard to. Actually, okay, yeah, no, this is great. So, there's this philosophical essay about what it means to be a bat.
Oh, I
So,
love that one. Yeah.
yeah, it's so good. So, like, and the answer, well, okay, the question is like, what does it mean to be a bat? Like, what is a bat experience? But the answer to that question is like, we'll never know because we'll never be bats, you know. So I think that it makes it really difficult to say like, okay, I have this cup, for example. What state spaces is this cup interacting in? I don't know. I've never been a cup. I can make a lot of guesses based on the tools that I have, and with science, and just as an observer. But I'll never know for sure. And also, it's really hard to think about all the different possible state spaces in absence of an observer. I mean, like, how? What are the number of ways that you can describe the world without being human? I like, you know, I think that's a really hard question to answer. So I definitely think those are some limitations.
Cool. So next we have a question from Madi. So Madi's asking, mental background can affect the way we see. Also, we have the same in illusion studies. Was the ancient Greek view maybe of the ocean due to illusions? Was it illusionary?
Yeah, I have no idea. That's a really cool question, and I'd really love to understand. Yeah, I would love to know the answer to that. Maybe I'll ask some of my perception friends about that, and maybe I'll post it on Twitter later.
Cool. That would be awesome. And you can follow Alyssa at Timo Do Science on Twitter. So please do that if you're interested in this kind of stuff. Okay, our next question is from Saulo, who asks, have you thought about designing an algorithm based on the models you've presented to implement true creativity?
Yeah, I'm always thinking about implementation for this kind of stuff, because eventually that's really what I want to do. Is I want to take these ideas about state spaces and be able to put it into a computer model and start, playing around. Like, do we actually get stuff like creativity? So yeah, I have been thinking about it a lot, and you know. One of the big reasons I didn't just like jump right on it is because I wanted to get these insights from data first, because I think I can, I can open up a new PyCharm file and just start typing away. But there's a lot of insights that I'm actually missing. And those insights, I want to I really want to understand what biology is doing so I can emulate biology and learn from it, in order to build my models that can accurately reflect what biology is doing. So I would really love to do it someday. Knock on wood, it'll happen soon. Yeah, always thinking about that.
All right, and then we have one more question so far. So if you do have any other questions, anybody in the audience that you want to ask publicly, go ahead and check out that Slido link that we've got over in the chat. But so the question is, what if smoothness isn't real and is a cognitive artifact of zooming out too far? Is that still a limitation or just a hindrance, or is continuity emergent?
Oh, yeah. I once asked a physicist who knew a lot about string theory whether reality is inherently continuous or discrete. And he thought about it for like 10 minutes and then he was like, I think it's discrete. Um, but he wasn't really sure. So I wasn't really sure. And I really have no idea. So, yeah, it's a great question. It's also really hard to think about these things because you're at least for me, what I'm trying to think about is I'm trying to think about like what reality is beyond my own perception, and that's like obviously impossible to
Mhm.
do. Um, but I think in terms of making wild guesses like that, my hope would be that a mathematical framework would be able to work even if those questions aren't being answered. I don't really have any ideas of what that might mean or what that could look like in terms of an implementation, but that's my hope, anyways.
Cool. I think that sounds like a lot of really exciting stuff. So that's all we have right now for questions on Slido. What I'm going to do is I'm going to invite anybody who would like to join us for a private Q&A on Zoom, and that link will be posted in the chat. So thank you once again to everybody for joining us this month. We'll be back next month with another speaker, and we hope to see you then.
Thanks, everyone.